Hey everyone, Houston Math Prep here to go over the method of undetermined coefficients for non-homogeneous second-order differential equations. We've got a y double prime plus by prime plus cy equals some function of x we're calling g of x. If this is a linear equation with constant coefficients, in other words, we assume a, b, and c are all constants, and for this equation to be non-homogeneous, then remember g of x needs to not be 0, so we don't have 0 on, say, the right-hand side of the equation. Then this is a case where we might use the method of undetermined coefficients. We want to make sure that we're already good at solving homogeneous second-order equations with constant coefficients, because the first step in this process will be to solve the associated homogeneous equation ay double prime plus by prime plus cy equal to 0. Solving this associated homogeneous equation will give us what we call the complementary function y sub c. And that solution would give us a true statement that this left-hand side is equal to 0. So what we'll need to do then is add in something to our solution, our y sub c, in order to make the left side add up to g of x, what is on the right-hand side. This extra piece of the solution that we add to the complementary function to solve the non-homogeneous version of the equation is called y sub p, the particular function. And our solution y equals y sub c, the complementary function, plus y sub p, the particular function. We just want to remind you that all of the terms in here need to be linearly independent from one another. The method of undetermined coefficients is used when we have some sort of an idea of a particular function y sub p that might satisfy this equation. And the way we might have an idea of what would work for y sub p, the particular function, will be to look at the form of the right-hand side. So if our right-hand side g of x is some constant, then our particular function will also just be some constant. If our right-hand side is a linear polynomial, then our particular function will also be a linear polynomial, which we'll call ax plus b. If it's a quadratic polynomial, then we'll need to have a quadratic term, a linear term, and a constant term. If our right-hand side function g of x is sine or cosine of some multiple of x, then our particular function is going to be some multiple of cosine of that multiple of x plus some other multiple of sine of that multiple of x. And lastly, if our right-hand side is just e to some multiple of x, then our particular function form will be some multiple of e to that multiple of x. And we'll just go ahead and work through these 5 examples for you now. Now you'll notice our left-hand side is going to be the same for all of these examples. We've done that to save time so we're not spending a bunch of time solving left-hand sides and focusing more on the undetermined coefficient method for the video. Let's look at our first one. We'll go ahead and solve the associated homogeneous equation. So remember our characteristic polynomial for y double prime plus 3y prime plus 2y equal to 0, right? Think about solving this. Then what we'll end up getting for this characteristic polynomial will be m squared plus 3m plus 2 is equal to 0. So we're solving the associated homogeneous equation. This factors into m plus 1 times m plus 2. And if we set each of these factors to 0 and solve, we'll get that m is equal to -1 and m is equal to -2. And remember from our homogeneous constant coefficients video, that tells us then that our complementary function is going to be c1 e to the -1x, or just -x, plus c2 times e to the second m value -2x. So this is our complementary function. And again, because we have the same left-hand side for each of our examples in this video, we're always going to have this same complementary function, at least in this video. Looking here at the right-hand side, which is the important part for the undetermined coefficients method, so our g of x here is 8. And if g of x is just some constant, then that means our y sub p just needs to be some constant. We're going to call it a. And think about, to plug in to this equation, I have y, but I'll also need y prime and y double prime. So if I take the derivative of yp, that will just give me, since a is a constant, that will give me 0. And the second derivative, of course, will also then be 0. So we take our information for yp, its first derivative and second derivative, we put it in the equation, and then we solve for our undetermined coefficient. In this case, we just have an a to solve for. So if we plug in here, y double prime is going to be 0 plus 3y prime. Y prime is also 0 here. We're just plugging in our yp and its derivatives, plus 2 times y, so in this case our yp is a, so we have 2 times a, is equal to 8. So we really just get that 2a is equal to 8. And that, of course, is going to give us that a is equal to 4 if we divide by 2. So that is my yp. I get that yp is equal to 4. And remember, my solution is simply going to be my complementary function plus my particular function. So in this case, we will have our y sub c, which is c1 e to the negative x, plus c2 e to the negative 2x, plus our yp, which is just 4. Looking at our next example here, we already know the complementary function that goes with this is going to be c1 e to the negative x plus c2 e to the negative 2x, because we already solved this previously in the video. In this case, though, now our g of x is a linear polynomial. It's no longer a constant, right? So our y sub p, our particular function, needs to have the form ax plus b. Multiples of this thing and its first derivative and its second derivative could give us these terms over here. So we go ahead and set up our yp as ax plus b. The derivative of this would just be a. The derivative of this term would be 0. And then the second derivative, so the derivative of a now, we're going to again get 0 here, right? So we take this information, we plug it into the equation over here. So y double prime is going to be 0 in this case, plus 3 times y prime, which is a, plus 2 times y, which is ax plus b. And that is supposed to give us 4x plus 5. Now let's go ahead and distribute and see what we have. So we have 3a plus 2ax plus 2b, if we distribute, is equal to 4x plus 5. Now at this point we want to compare coefficients of each term on both sides. So I'm going to go ahead and combine like terms, my 3a and 2b. Those are constant terms. So over here I'm going to say 2a times x plus 3a plus 2b. So it's easy for me to see how many x's I have on each side, how much constant I have on each side, right? So you can see here, how many x's do I have over here? I have 2a. How many do I have over here? I have 4. So that tells me, right, that 2a should equal 4. And then here, I should have the same amount of constant on each side. So 3a plus 2b should be the same as 5, right? So 3a plus 2b is equal to 5. Now I just need to solve for a and b. I think if I solve this first one here, dividing both sides by 2, that's going to give us that a is equal to 2. And then once I have the a is equal to 2, I can take that information and plug it in here and solve for b, right? So that would give us 3 times 2, so in other words 6 plus 2b equals 5. And if we subtract the 6 and divide by 2, we'll get that b is negative 1/2. I can take my a and b information, I can put it in there. So I know now that my y sub p is actually 2x minus 1/2 if a is 2 and b is negative 1/2. And now we'll go ahead and write our solution, which is y sub c plus y sub p. So in this case, our complementary function was c1 e to the negative x plus c2 e to the negative 2x, plus our y sub p, which gives us plus 2x minus 1/2. For our next example here, we have the same left sides. We'll go ahead and write down the same y sub c. So this will be c1 e to the negative x plus c2 e to the negative 2x. And again, if you skipped the first example, we solved it back there. So you can go ahead and check that out. Here, this is our g of x, our right-hand side. So because we have a quadratic polynomial, that means our y sub p in this case is going to be ax squared plus bx plus c. And then the derivative of that will be power rule here, right? 2ax plus b, c is a constant, so nothing there. And the derivative of that is going to be just 2a. So we take all of this information, we plug it into our equation and solve for a, b, and c. So our y double prime is 2a plus 3y prime, so plus 3 times 2ax plus b, plus 2y, so plus 2 times ax squared plus bx plus c. And all of that equals the right-hand side, right? 2x squared plus 4x plus 5. All right, we'll go ahead and distribute our left side and combine everything. So we get 2a plus 6ax plus 3b plus 2ax squared plus 2bx plus 2c is equal to all of this on the right. Now, this is the only x squared term that we have, so we'll just go ahead and say 2a times x squared plus, now all of my x terms, I have a 6ax and a 2bx, so I'm going to say 6a plus 2b x, and then all of my constant terms, 2a, 3b, and 2c. So we'll say plus 2a plus 3b plus 2c is equal to 2x squared plus 4x plus 5. And so now we will compare the coefficients, right? So this here says that 2a should equal 2, so we have that. 2a is equal to 2. And this says 6a plus 2b needs to equal this amount of x as well. So 6a plus 2b is equal to 4. And our constants should be the same on both sides. So 2a plus 3b plus 2c is equal to 5. So we'll just go in order of least amount of unknowns to greatest amount of unknowns. So solving this first one, 2a equals 2 is going to give us that a equals 1. And if we plug the 1 in for a in the next one, that will give us 6 plus 2b is equal to 4. Go ahead and subtract your 6 and divide by 2. That will give you that b is negative 1. And then if we take a as 1 and b is negative 1, we put them down in the last one. That would give us 2 minus 3 plus 2c is equal to 5. So we'd get negative 1 plus 2c is equal to 5. Add 1 to both sides. That would give you actually 2c is 6. Divide by 2. That would give you that c is 3. So we get our particular solution there with a equal 1, b equal negative 1, and c equal to 3. That is ax squared would just be x squared, plus bx would be minus x, plus c would be plus 3, right? So this is our ax squared plus bx plus c that we assigned for yp at the beginning there. We now take our y sub c and we add our y sub p to it. Remember, y is going to equal our complementary function plus our particular function. So we'll say y is equal to c1 e to the negative x plus c2 e to the negative 2x plus x squared minus x plus 3. For our next one here, we have the same left-hand side, so our complementary function that, again, we already solved and did the work for in our first example. So if you've skipped straight to this example, you can go back and check out how we got this y sub c. But that's our y sub c. Over here on the right-hand side, our g of x is cosine of 2x. So that tells us that a y sub p that would have multiples of itself and its first derivative and its second derivative, being some multiples of cosine 2x, would be a times cosine 2x plus b sine of 2x, right? Think about the first derivative of sine as a cosine, right? And we have a first derivative here, so certainly we need this additional as well. We'll need the derivative and the first derivative of our y sub p. So here the derivative of cosine is negative sine. Chain rule gives us a 2, so we'll get negative 2a sine of 2x for that term. Here we'll have derivative of a cosine. Chain rule will give us a 2 though, so we'll have plus 2b cosine 2x. Taking the derivative of that, y sub p double prime, here we'll get cosine there, another 2 will come out, so we'll get negative 4a cosine 2x for that derivative. Here we'll get negative sine, another 2 will come out, so we'll get minus 4b sine of 2x. So that's our y sub p, its first derivative and its second derivative. We'll have to take that and plug it into the equation. We've got a lot of terms to plug in. We'll go ahead and try to save some space here. So plugging in y double prime first, we get negative 4a cosine 2x minus 4b sine 2x plus 3y prime, so plus 3 times, now plug in y prime of p, which is negative 2a sine 2x, plus 2b cosine 2x, plus 2y, so plus 2 times the original yp, which is a cosine 2x plus b sine 2x. Okay, that's all the left-hand side, equal to our cosine 2x, our right-hand side. So equal to cosine 2x. Now we'll just go ahead and distribute everything. And then we'll combine all of our like terms and compare side to side. So keeping these first two distributing, the 3 will get negative 6a sine 2x plus 6b cosine 2x. And then distributing the 2, we'll get plus 2a cosine 2x plus 2b sine 2x equals cosine 2x. We can just fit it in there. Now let's go ahead and combine all our sine terms and cosine terms, get them all together, and then we'll compare one side to the other. So I have a cosine term here, and here, and here. So if I think about, I have negative 4a plus 2a, that would give me negative 2a, and I have 6b, so I have negative 2a plus 6b cosine 2x. So that's all of those terms. Now look at the sine terms, so I have that one there, and that one there, and that one there. So I have negative 4b plus 2b would be negative 2b, and then I also have negative 6a, so we'll go ahead and say negative 2b minus 6a sine 2x equal to cosine 2x. And now we'll give ourselves some room, and we just want to compare both sides, right? So over here, what do I have? Well, I have this many cosine 2x's. How many do I have over here? I really just have 1, right? So that tells me negative 2a plus 6b is equal to 1. And for sine x's, we want the same on both sides. Here I have negative 2b minus 6a. And over here, I don't have any sine 2x's, right? This is really like having 0 sine 2x's over here. So these coefficients must be the same. I'm going to go ahead and turn these around so they're in alphabetical order here. So I'm going to say negative 6a minus 2b, that's just this with the terms reversed there, is equal to 0, because that's how many sine 2x's I have on the right side. And I can't really solve either of these just all at once, right? This is sort of a system of equations that I need to deal with. So maybe I go ahead and notice I have a 6b here and a negative 2b here, so I could eliminate the b's by multiplying the bottom equation by 3, and then adding these together. So let's go ahead and do that. So we'll keep the top equation, negative 2a plus 6b is equal to 1, and if I multiply the bottom by 3, we'll get negative 18a minus 6b still equal to 0, and when I add these together, we get no more b's, so we get negative 20a is equal to 1, and then dividing by negative 20, that's going to give us that a is equal to negative 1 over 20. And so I have a, I need to go find b. Maybe I'll plug this negative 1/20th into the bottom here. So negative 1/20th times negative 6 would be a positive 6 over 20, minus 2b is equal to 0. If I add the 2b to the other side, then that gives me 6 over 20 is equal to 2b. And dividing both sides by 2 or multiplying by a half is going to give me 3 over 20 is equal to b. So I have negative 1 over 20 for a and 3 over 20 for b. And just make sure that you remember which was which, right? Our y sub p was a was with cosine x and b was with sine x. So this tells us that our y sub p is going to equal negative 1 over 20 cosine 2x plus 3 over 20 sine 2x. So we combine that with our original y sub c. So remember, y is going to equal y sub c plus y sub p. And remember, our y sub c was c1 e to the negative x plus c2 e to the negative 2x. So then we'll get minus 1 over 20 cosine 2x plus 3 over 20 sine 2x. Looking at our next one here, we'll have the same complementary function that we've had in all the other ones. So y sub c is c1 e to the negative x plus c2 e to the negative 2x. Here our g of x is e to the 3x. So remember, the idea with the form is what function in some multiples of its first and second derivatives will give us e to the 3x maybe, and that would be some multiple of e to the 3x. So our y prime here is going to be 3a e to the 3x from the chain rule, and then chain rule again is going to multiply by 3 one more time, so our yp double prime is going to be 9a e to the 3x. We take all this information, we put it in the equation, and solve for our a. That's our undetermined coefficient. So we'll get 9a e to the 3x plus 3y prime is plus 3 times 3a e to the 3x plus 2y, so we get plus 2 times a e to the 3x is equal to e to the 3x. These are all going to be like terms over here, right? So we get 9a e to the 3x plus another 9a e to the 3x plus 2a e to the 3x is equal to e to the 3x. Combining all of those, we get 20a e to the 3x is equal to e to the 3x. And now just compare your coefficients, right? I have 20a over here. What's my coefficient here? This is really like a 1 here. So that tells me then that 20a is equal to 1, dividing by 20, of course. We'll get a equals 1 over 20. And now we can write our solution. Remember, our solution is going to be y sub c plus y sub p. So taking this 1 over 20 and putting it back in for a in our yp, we'll have that y is equal to c1 e to the negative x plus c2 e to the negative 2x plus a e to the 3x becomes 1 over 20 e to the 3x. And we just want to point out one additional thing here in the video. Let's say we had an example like this. We're not going to work this out fully. It has the same left-hand side though, so we know that y sub c equals c1 e to the negative x plus c2 e to the negative 2x. And based on this here, we would say that yp maybe is a e to the negative 2x. But we don't want to use that because this term is not linearly independent with my c2 term. Notice this is some constant multiple of e to the negative 2x. This is some constant multiple of e to the negative 2x. So we would not choose this as the form for our y sub p. These are not linearly independent. Remember, when we run into this, what we'll do to actually create linear independence is we'll multiply our y sub p by x. And so our actual y sub p that we would choose would be actually ax e to the negative 2x, and we would then solve this problem going off of that y sub p. Our next video is about solving with undetermined coefficients when we have issues that deal with linear independence like this, so you can go ahead and check out some more information about that in our next video. Thanks for watching, everybody. We'll see you then.